In this lesson, we're going to talk about random variables, and specifically we're going to talk about discrete random variables and then the corresponding discrete probability distributions. So first of all, when we conduct an experiment with outcomes that have associated probability, so we're doing some kind of experiment that has, randomness in it, and we describe those outcomes with numbers. So the outcomes that are occurring are associated with numbers in some way. Then we call the set of numerical outcomes, and the set of numbers that we could get, we call that a random variable. And we use a capital letter to represent the random variable, like capital X or capital Y or capital Z or whatever it might be. So for example, if I toss two coins, then a random variable would be, for example, X could represent the number of heads that we get after we toss the two coins. So it could be 0 heads, 1 head, or 2 heads. It's a variable that represents the number of outcomes, or number of heads in this case, listing out the outcomes with a number. Now this is not a random variable, which would be the outcomes that occur are heads, 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 tails, tails, heads, or tails, tails. These are not numbers. There's no numerical value associated with these outcomes. So this is not a random variable, but the list of number of heads that might occur, that is a random variable. In this case, 0 heads, 1 head, or 2 heads. Now a discrete random variable is a random variable that takes on values that have gaps between them. So you can have 0 heads or you can have 1 head, but you can't have 0.76349 heads or 1.2186 heads. So this is a discrete random variable. Typically it's because we counted the outcomes that occurred. Now a continuous random variable would be one that can theoretically take any value in between. Usually it's done by measuring again. We could do a random variable that represents the heights of students at a school. And of course there are probabilities for people having heights between this height and that height. So between 5, 6, and 6 feet, there's a probability that there may be students in that category. And again, by measuring there in that scenario, you're limited only by your measuring tool, and therefore we can consider the random variable of height being measured is a continuous random variable because technically, based on the precision of my tool, I can get as many decimal places as I would like. So that's a continuous random variable. Now in this particular lesson, we're going to stick with the discrete random variables for now. So here's an example. A supermarket has 3 checkouts, A, B, and C. An inspector checks the weighing scales for accuracy at each checkout. The random variable X is the number of accurate weighing scales that are found. So each scale is either accurate or inaccurate. And so the outcomes are each time accurate or inaccurate, but the random variable X counts out or lists the number of scales that were found to be accurate. So the first question is list the possible outcomes of the experiment and the corresponding values of the random variable X. So what I've done here is I've created a table for A, B, and C, and in here I'm going to have all the combinations of accurate versus inaccurate, and then X would represent the number that I found in each particular scenario. So I'm going to use Y for yes, it was accurate, and N for no, it was inaccurate. So one possibility, of course, would be all of them were inaccurate. So no, no, no. Then I could have yes, no, no. Then I could have no, yes, no. Then I could have no, no, yes. They could have yes, yes, no. I could have yes, no, yes. I could have no, yes, yes. And then I could have yes, yes, yes. And that's all the possibilities. And now the random variable, on the other hand, is how many of these were accurate each time. So in the first column, 0 were inaccurate, 0 were accurate. In the next one, 1 was accurate, 1 was accurate, 1 was accurate. And then there were 2 accurate, 2 accurate, 2 accurate, and finally 3 accurate. So now the next part of the question says, what X value corresponds to exactly 1 accurate scale? Well, if there's exactly 1 accurate scale, then X equals 1. Now there are three different ways that could happen. Either the A scale was the accurate one, or the B scale was the accurate one, or the C scale was the accurate one. But the value of the random variable doesn't care which one was the accurate one. It just cares about the fact that one of them was accurate. So x equals 1. Finally, what x values correspond to at least one accurate scale? And I don't care which ones, but at least one would be x could equal 1, or x could equal 2, or x could equal 3, and there's no more than that. So it's everything here on out, just not this one. Not having 0 accurate scales, but having 1 accurate scale, or having 2 accurate scales, or having 3 accurate scales. Again, what I'm trying to highlight here is that the random variable doesn't actually care which of these are accurate, which are not. It's just how many of them are accurate that we care about when you're dealing with the random variable, because it has to be a numerical value. So now let's talk about discrete probability distributions. So if x is a random variable, discrete random variable, and it has possible values x1, x2, x3, etc., how many ever there might be. So in the previous example, 0 scales, 1 scale, 2 scales, or 3 scales that were accurate. And then we have corresponding probabilities. So the x1 has a probability of p1, x2 has a probability of p2, and so on. So these are the different probability values, such that the probability that the random variable is equal to the x1 value is equal to p1, and the probability that x equals to x2 value is equal to p2, etc. So the probability that x equals xi is pi. So this is just a list of all the outcomes that are on the random variable, so numbers. And these are the probabilities that match. That's all we're saying over here. Then there's two things we know. The first is that all the probability values are somewhere between 0 and 1. It's possible to have a probability value of 0. That means that thing did not happen. It's possible to have a probability of 1. That means that thing is guaranteed to happen. And anywhere in between is okay for all of these probability values. That's what this is saying. The next thing is that when you add up all of the probability values, you need to get 1. Because if this is the list of all the possible things that might happen, well, if I add all their probabilities, one of those things is guaranteed to happen because these are all of the possibilities. Therefore, adding up all the probabilities should end up giving you 1. So these are the two rules for getting a discrete probability distribution. That the probability values, each individual one, is somewhere between 0 and 1. Could be 0 or could be 1. And that when you add up all the probabilities, you must get 1. Then this list of probabilities is called, it describes the probability distribution of x. It shows you how the probabilities are distributed for the different x values. Now, this is not the usual way that we list the probability distribution. We tend to do it in different ways. I'm going to show you two examples of how we might list probability distributions. So here, if we toss 2 coins and x is the number of heads that occur, then here's one way to list the probability distribution. That's to have x equals x, 0, 1, or 2. Those are the number of heads. The probability that x equals x. Now, the probability of getting 0 heads is 1/4. That's the tail-tail scenario. The probability of getting 1 head is 2/4 because it's heads, tails, or tails, heads. And the probability of getting 2 heads is 1/4. Now, all of the probabilities are between 0 and 1, 1/4, 2/4, 1/4. And if you add them all up, you get 1. 1/4 plus 2/4 plus 1/4 is equal to 4/4, which is equal to 1. So this is indeed a probability distribution, and it represents the probability of getting 0 heads, 1 head, or 2 heads when we toss 2 coins. Now, the same information that's in this table, I can do it in a graph. The probability is the vertical scale. The x values, or the random variable values, are the horizontal scales. 0, 1, and 2 are the things that might happen. 0 has a probability of 1/4. Put a rectangle there to represent that. 1 has a probability of 1/2. Put a rectangle there to represent that. And then 2 has a probability of 1/4 again. Put a rectangle there. And again, all these probabilities are somewhere between 0 and 1. And if you add them all up, you get 1. Now, just so that we've seen it, it's pretty common, so you recognize the name. A uniform discrete random variable, y, let's call it, I'm just changing variables here on us for a second, is a discrete random variable where all values of y have the same probability. So the heads and tails one, where we're counting the number of heads with 2 coin tosses, was not uniform because different values had different probabilities. However, If I roll a six-sided die, a regular six-sided die, then each of the outcomes, 1, 2, 3, 4, 5, or 6, which are numbers now, so I don't have to like find a number for it. It already is numbers. Each of them has a probability of 1/6. Therefore, this is a uniform probability because all the values of the random variable have the same probability. So now let's talk about the mode of a discrete probability distribution. Similarly, when we were looking at data, the mode was the value that occurred the most. Now there may have been more than one depending on how you counted that, or there may have been none. But here, the mode of a discrete probability distribution is the value of the random variable, the value of x or y, whatever it might be, with the largest probability. So here probability just means it occurs more often. It's more likely to occur. So this example over here had no mode because they were all with the same probability, whereas the tossing two coins, one head was the mode because it had the largest probability. The median of a probability distribution, similar to the median of a list of data, is the 50th percentile of the random variable. So what you have to do is you have to list the random variable in increasing order. So you and then you list their probabilities. So this is an example of that. And then you're looking for, when you add up going from the lowest to the highest, you keep adding the probabilities. Once that sum reaches 0.5 or a half, then you have hit the 50th percentile, and then you would know what the median is. Now this is easiest to understand with an example. The mode is relatively straightforward. Median takes a little bit more brain power, I suppose I would say. So let's go ahead and do it with an example. All right, a magazine store recorded the number of magazines purchased by its customers during 1 week. 23% of the customers purchased one magazine, 38% purchased 2 magazines, 21% bought 3 magazines, 13% purchased 4, and 5% bought 5 magazines. The first question is to identify the random variable and list its possible values. So I could use any letter I want, so I'm just going to use capital X because after all, that's the one we tend to use. So capital X, so it has to be something that's a number. So the magazine store recorded the number of magazines purchased by its customers. So that sounds like a random variable. The number of magazines purchased by a customer. That is the random variable because it's either 1, 2, 3, 4, or 5 magazines. And now I want to list its possible values. Well, in this case, I just gave it away. X could equal 1, 2, 3, 4, or 5. Now you might say, well, what about 0? Well, if the person purchased 0 magazines, and magazines is the only thing that these people sell, then they weren't a customer. They may have walked in and browsed and then left, but they're not technically a customer until they bought something. So having 1 being the smallest number of magazines you could purchase makes sense. Now this next question wants us to construct a table for the probability distribution. So again, I'm going to have X and the probability that X equals X. And I'm going to have 1, 2, 3, 4, or 5. And now underneath these, I want to list their probabilities. Well, the probability of getting 1 was 0.23. Remember, we don't really want to work with percents. We want the decimal version. So 23% purchased 1 magazine, so 0.23 is the corresponding probability. 0.38 is going to be the probability of a person who purchased 2 magazines. 0.21 is going to be the probability of buying 3 magazines. 0.13 is the probability of buying 4 magazines. And 0.05, 5%, is the probability of purchasing 5 magazines. Now, there's a couple things we want to check. Are all these probabilities between 0 and 1? They are indeed. And if I add them all up, do I get 1? And you can double check this, but you will indeed get 1 when you add all those probabilities out. Part C now wants us to graph the probability distribution. So what I've done here is I've put the values of X, or the random variable, on the horizontal scale 1, 2, 3, 4, and 5. and then I've put probabilities on the vertical scale, and you never squiggle on the vertical scale again. So 0.1, 0.2, 0.3, 0.4 were the probability scale. Of course, none of those values were exactly those, but that still gives me a scale. And now I can either draw rectangles or I can just draw vertical lines, which are called spikes. So in this particular case, just so that you've seen the variety, I'm going to use the spike version. So all we do is we go to the 1 and we have a spike that goes up to 0.23. And then over the 2, we have a spike that goes up to 0.38. And then over the 3, you have a spike that goes up to 0.21. And then over the 4, we have a spike that goes up to 0.13. And finally, over the 5, we have a spike that goes up to 0.05. So this again is called a spike graph for the probability distribution, but basically just has the x values and then the probability values are the vertical scale. And instead of drawing rectangles, I drew spikes. So again, if you don't like the spikes, you could draw rectangles instead, like I did in yellow here. Make sure they don't touch because these are discrete values, so that rectangles should not touch. One of the advantages of the spikes is that they can't touch, so it's obvious when you do spikes that you're dealing with the discrete random variable. Finally, let's talk about the mode and median of the random variable, where the mode is whichever value of the random variable has the largest probability. Well, obviously this one, so x equals 2. So the mode is x equals 2. Now the median. So to get the median, what we do, they're in increasing order, 1, 2, 3, 4, 5, the random variable is. So we start adding up probabilities until we pass 0.5. So obviously 0.23, that first number is not bigger than 0.5, so we haven't hit the mode yet. But let's add 0.38 to that. Well, 0.23 plus 0.38 is 0.61. So that means that we've now went from 23% up to 61%. So we've passed the threshold of the 0.5. It was somewhere in the middle of this region. So when x equals 2. So the median occurred in that 38% spot when x was equal to 2. So we accumulated probability until we passed the 0.5, and we said, okay, when was it when we passed the 0.5 in this case? When x was equal to 2. And that is the end of the lesson.